Okay, so now we are recording. First, today we are going to be doing some, let's say, admin about how the next few weeks are going to go. So let me share my screen too. Yeah, this one. Now you will be seeing some past AI page, which I will get to a little bit later. Okay, so today is Tanabata actually in many parts of Japan, the Star Festival, but that's not what we are here to discuss. Today is the 7th of July. As you can see in web class, the deadline for project number 3 is the 28th of July. So exactly 1 to 3 weeks from now. 3 weeks from now, we will have our usual questions and answer session for the last day of one of the programming projects. Okay, and today, as I said, we're going to be completing the last important, mandatory, big part of what we are going to be saying about deep learning networks with the training. Okay, that leaves us with a couple of, let's say, slightly weird days. So next week we had time for a lesson, but I will be traveling, so there will be no main lesson next week. Okay, I will probably give you some, let's say, recommended reading for um, for next Monday from the notebooks that are already there. And if there is some petition, I might add something extra during this week if anyone needs it. Okay. And officially, that should be it. On the because the 21st is a holiday. Okay. On the 24th, I think, yes, on the 24th, here in Yamagata, we have a day where we also have classes that should have happened on Monday. Okay, so again, if anyone needs some extra content and so on, or there is something that you want to discuss about, I'm absolutely open to doing that. Okay, I will post this all in web class, but officially today is the last, let's say, full theory class, and then we can have some more specialized things if there is something that you're interested in, and then we will have the final questions and answer session. And in that one, as usual, I will be open to receiving questions and answers, and I will be doing some other content in class in case there are no questions and answers asked. Okay. So far, I have received some questions about project number 3, but I haven't received much code yet. Okay, so have a look at it. Project number 3 is not difficult, I would say. It's complicated, it's complex, it has many pieces. If you have made it this far, the data preparation tasks, which are the most annoying, should not be too difficult for you. So you should be able to complete those. And from there on, it's mostly a matter of reusing code with very little modification. And today I will say a little bit more about the modification regarding the data sets. Okay, I'm talking about the general version of the project. Nowadays, we have several alternative versions of the project. Okay, I'm here in the notebook for the project, which was updated last week a couple of times. So first we have the visualization of the data as usual, sorry. The function to build the ground truth and the function to get the treetops. So task 1 is about making patches using these two types of data, okay? But you have an alternative task 1 where you should make boxes and sorry, tiles first and then boxes within those those tiles using the box files that are already there. If you're doing alternative version number 2 about object detection. You should also be doing tiles and the type of ground truth image, label image on each of the tiles if you're doing alternative version number 2 about semantic segmentation. Finally, if you're doing alternative version number 3 about regression, then you need to do anything related to these images here, but you need to go and check the data generation notebook where we create those checkerboard patterns images. Okay, so task 1 is about generating the data, and for most of the projects and alternative versions of projects, that means modifying what you did already in project number 2. Okay, in order to get the proper patches or in order to get the tiles. You have the create patch function here in order to create the patches that you need. Okay. In task number 2, you will be doing data sets for your for your problem. Okay, and I will be speaking a little bit more about this using notebook, the 4th notebook in the let's see, let me show you in the course page, which will be more informative. So using the computer vision and deep learning course, unit 4, okay, handling custom data in Pytorch. This is absolutely parallel to what you need to do in task 1 and 2. 1 is a little bit more separate, but 2 is very similar. But there are some differences which I will talk about in a second, okay? That's for the general version. You need to do a small modification, which I will talk about today. If you're doing semantic segmentation, this is a little bit more different. Here, what you need to do is do an init method where you prepare the data by cutting the mosaics and big label images of the same size of the mosaics into tiles and label image tiles. And then for in each get item, so you have to do the preparations for that here, probably create the tiles and the image tiles and the label image tiles, and put them probably in some list of tiles and label images. And then in get item, you have to either access that list, or here you store the images to disk, and here you read them from disk and return them. Inputs will be an image and targets will be label image in this case. Right, jumped object detection there. Object detection, you will need to the same thing, create the tiles in the same way exactly, either by putting them all on a list or storing them to disk. And instead of label image tiles here, you will have box tiles, okay, box list tiles. So for every mosaic, you will need to cut it in small pieces, in these small tiles. And then for each tile, you will need to be aware of what boxes fall inside of that tile. Okay. I'm going to give you 1 minute to think about what the difference is between just reading all the images here in in the init method of the dataset class, okay? So like we are doing here, okay? In this version, we are reading everything here, okay? So at the end, this, as we will see, image list will contain lots and lots and lots of images. And in get item, we just return those images that we already have in memory, in RAM memory, okay? What would be the difference between just creating this image here, writing it to disk here, and making a note in my list of the name of the image, and then reading it here, okay? I said I'm going to give you a minute. I'm going to give you a little bit more. I'm going to continue with the explanation, and now when we get to the data sets, I will tell you the answer about this. And if I forget, please remind me. Okay, and in the final one, in the regression example, what we need to do here is generate data. Or, well, if you have already generated the data in task number 1 and you have images on a folder, then here you can also just read them, but you have to, in this case, read the checkerboard images, and for each of them be able to count how many of the, let's say, interesting color, probably if the background is blue and the interesting thing is in red, so how many red colored squares are there in the image. Okay. So either you have already made a note of this when you were generating the data and you have it in a nicely neat file. That's the way I recommend in the alternative description, or you just store the image and here you count how many red squares are there. Okay, which also works, but probably a little bit more complicated. Okay, so we are going to be speaking a little bit about this today, and the alternative descriptions of the data are, sorry, of the projects are here, okay? Some of the projects, I think it's probably one, so the general one and the alternative version one have a going deeper task, okay? This first version about image classification can be a little simple if you are already seasoned programmer. So if you feel that you have gotten to task 4 and it was a little bit simpler, you can go deeper by trying other deep learning networks and by playing a little bit about with the training and validation data. Okay, and this difference between training, validation, and testing is one of the things that I'm going to be speaking a little bit about today, but hopefully in the sessions that remain, we can go a little bit deep into that because it's quite important. Okay, so alternative version 1 with all of its tasks that I was mentioning about object detection, 2 about semantic segmentation, okay, and here you have the detailed explanation of what I was mentioning now quickly. If you have any questions about this, just let me know. And project number 3 about regression. This project has, let's say, 2 alternatives in itself. The first one is that if you just generate the data, can do that, and then group the data into classes, like for example, this class has a few, a lot, many, doing like a gradation, almost none, red pixels in it, red squares in it. So instead of predicting the number of squares that will be in image, if we start by predicting the category among a gradation that we made up, then the tasks about training and testing are just exactly as in the image classification. We transform this into an image classification problem, and that's easier, okay? So you generate the images, checkerboard images, and then group them into different classes. Okay, those who have fewer red pixels, red squares to more red squares into as many classes as you want. My recommendation is that you check the minimum number of red squares and maximum number and use that to make as many classes as you want. Okay, and then what you have left is a image classification problem, and that's solved in the notebook that we are going to be reviewing just now. After that, after you have that, then it's not that difficult to change, to fine-tune the thing to do regression. The only problem is that to do regression, you have to modify the network itself, the architecture of the network itself. In this case, it's just modifying the last layer, the classification layer, and transform it into a linear layer with the correct number of inputs, and that's detailed here, okay? Sorry. Yeah, here, okay? So, so not here in the training one, here, okay? So uh, in order to modify the network, you need to define a linear layer in the end, and it has to have the proper number of input features, but that's given by the network that you're modifying, okay? So you have here basically the modification that you need to do, but you need to understand where that goes and what that means. And let's say that's a little bit more involved, okay? But relatively simply, if you understand how the data generation works and what the data is, you can generate the data, do a image classification problem, and then with this, you get the regression that is the final goal of this, okay? Okay. So far, a little bit by necessity, this whole thing has been a little bit abstract in terms of the code. I have been hinting at lots of things, but I haven't been able to play too much with the code because I didn't want to give up the solution. Okay. I'm going to be using this unit 4 to just run a little bit the code and be able to um, show you just some of the details that you're going to be needing. First of all, we have the data download and general images from a unit where the data manipulation was on the creation of patches and so on. You can also check that one if you are stumped in your task 1. Okay. There are some imports here which are necessary. We will be using NumPy because we are working with images as arrays. And we will be using regular expressions. Okay, regular expressions are just one of the many, many cool things that Python does that can make the code very compact and very efficient. But they are something that you might not have seen before. Okay, so I'm going to tell you a little bit how they are working in the code and also how to ignore them if necessary, if you're getting just confused by them, which might happen. Okay, we're importing the Pytorch dataset, of course, which is what we are going to be needing today. And in the unit, I have made an explanation where the dataset kind of grows. It starts with absolutely nothing. So in this stage, my CP dataset does exactly the same as the dataset, just a subclass of the dataset class from Pytorch, which we have imported a little bit higher up, I think. No. Okay, let me see. Oh, here. Okay. So this dataset that we are talking about is the dataset from Pytorch, Torch Utils Data Dataset. Okay, this class that we said last week allows us to communicate with Pytorch, to let Pytorch know how our data looks like and how it should take it to be fed to the GPU in the most efficient way possible. Okay. And as I was saying, this is kind of growing, but I'm jumping to the end. I heartily recommend that you have a look at that in detail if you haven't done so yet. Okay, so I can run the last version of the dataset. And in this last version uses here this regular expression thing. Okay. When I downloaded the data, I got all of these files and this folder patches where we have this kind of images for this unit. Okay, and each of them has a name that includes the word patch and includes one category. In this case, we have several names of species, and for example, Inutsuge is one of them. So Inutsuge patch 100.jpg means that this image belongs to the Inutsuge class. Okay. In our dataset, in the init method, what we do is read this patches folder and organize how the information is going to be fed to the GPU when Pytorch asks for it. Okay, and essentially here I have lots of images, lots of patches like you will have in your project, and I want to know where they are and store them and prepare them. But for each patch, I also want to know what class it belongs to. Okay, as I said before, one I opened before was Inutsuge, but there are other names around here. Let me go a little bit down. And for example, here we have Kaede patches. Okay, this thing is another species called Kaede, and so on and so on. We have 6 different species. Okay, so what this is going to do is have an image list that will store all of the images, a label list which will store for each image in the corresponding position the name of its class. Inutsuge, Kaede, it will be a string with the name of the species. Okay, and then we will also have a dictionary to store class codes. This is a little bit technical, but I cannot give my class labels as strings to Pytorch. So I cannot give Inutsuge to Pytorch or Kaede to Pytorch because that's going to be annoying it no end. So instead of that, I'm going to say the first time I encounter a new class, I'm going to give it the code 1. Okay. Second time, I'm going to give it the code 2, and so on and so forth. And this dictionary will have that information. When I said, what's the code for Inutsuge? It will return 1, supposing we found Inutsuge first. Okay, so let's leave it here for a second. Let's run. We have here a function that creates the data set. Okay, and then it breaks it into train and validation. It breaks it into 2. Okay, and here we can show the images that we have created. In this case, we are showing 10 images, okay, which appear here. But the important part is that here I have created the data set. So let me just add a print function here, okay, to see that I'm actually processing all of these files, okay. Then I can run this, okay. Unexpected event. What did I do? Oh yeah, I didn't indent it correctly, so I added an error. Okay, let's go again. And now here I can create, and here I'm printing all the names of all the images that I'm processing. Okay, so I have all of those already processed. But let's have a bit of a closer look. What am I doing in each case? I'm using these regex things, and I'm compiling a regular expression. Regular expression is something that tries to match patterns inside of character sequences, or in our case, strings. And what it does is that it finds the patch substring inside of file name, and then it's supposed to have something this means that this is numerical and might have 1 or more occurrences. Okay, so this might be 1 or more numbers, and then it will have a .jpeg. So for example, something that has patch and then 317.jpg works. Something that has patch 318.jpg works. 32, yes, if there was patch 1, that would also work. As long as we have at least 1 numerical character and then .jpg, this will work. But more importantly, I have this code here for regular expressions that basically stores, okay, locates whatever is before all of these patterns. So whatever is before patch. And before patch, what did I have? I had the name of my class, okay? So when I called this if regex match, regex is this regular expression, then this enters here. And then by doing split and getting this regression and getting the first component, or the second component in position number 1, from here I get the current class. Okay, so I get Kaede, Nanakamado, and so on. Okay, so where I printed, I was processing all the files. I was looking at all the files if I print here, I can print the file name, and let me also print the current class just to check what current class. Yes, just to check that when I create a data set, this is properly reading the class from the file name. Okay. And you can do exactly this if you want. If you are extremely lazy, you can just store your patches with the same names. So they will not be called Kaede or anything. They will be called probably 0, 1 for the code for the species, but you can do just that. Store them as 0, 1, patch, something, something, and then this will read them automatically without doing anything else. Okay. If you store them with other names, you can just, let's say, avoid the use of the regular expressions. Okay. Let's say I do not want to use them and I just want to process the the names of the files. Okay. Then I can do something like instead of whether this is match or not, I can just check whether or not the file name contains patch. Okay, sorry, file. Then I will still only get into this loop if I am in one of these patch files, okay? And then what do I want to do? I want to extract this part here before patch, okay? So I can do something like just let's find patch. That will be the index where I have to finish, and then I just want to get everything before that, okay? So let's say, well, I'm going to do it in one line because I think this is easy enough. So I'm going to do find patch in file. This is going to be the index of this position where patch starts. And then what I want to do is to get the file from 0 to this position where patch starts. Okay. Okay. And this should be doing the exact same thing. Okay. So I'm getting rid of the regular expressions, and instead of them, I'm using just regular string manipulation. Okay, let's see if that works. Again, we are doing the exact same thing. Okay, so in task number 1, you will store your data into files in a way that you like, and in task number 2, when you build a data set, you have to pick and choose the information from that data file and give it in a convenient way to Pytorch. Okay, first of all, for example, you have to get the class from the name of the file. You can use regular expressions if you want. You can use as I have just done, just regular old string manipulation. Okay. After you have done this, for each image you have the image, the patch, and you have the category. Okay. This is our basic unit of information here, our basic data unit, which will be giving to Pytorch in the getItem method. Okay, and what we are doing here is that we are preparing things to make that possible. As I said before, we have one image list and one label list. Current class is the label for the image in this file, in file. Okay. So what we do in this case is that we read the image from the file name, okay, and we add this image to a list, okay? So we are adding image to the image list, okay? To be fully precise, we're doing something different here too. We are moving the axis, okay? We are changing the axis in order to give them to Pytorch, okay? The way Pytorch expects the information to be stored and the way OpenCV and most image processing networks store, image processing libraries store the images is different, okay? So there is this technical thing that I recommend that you do, okay? Usually you should concern yourselves with the name and the label and so on, and this you don't need to modify very much, okay? But I said before, with this, I'm at the end of the init method. Once I have initialized, I have a full image list. I have all my images as big sequences of bits stored in a list. Okay. What's the difference of just storing here a current image name and then reading it here? Because I could do it. So here I could just not read the image, not have it read here, but have the name added to the image list. And then in getItem, in this case, what I do is just access image list of my current index, and that is my input, okay? I have to transform it to float also because Pytorch expects things to be stored in a certain manner and also be floats. They cannot be integers, which depending on how we have read our images, they might be. Well, they will most likely be images, but with this, we transform them to floats, okay? And in getItem, my unit piece of data, my unit piece of information is also always composed of the data itself, the input, but also the output, the desired response, the correct answer for that data. In this case, this is the target, the label, okay? Here we are classifying these kind of patches, each of them into one class. This will be KAED. So when I do getItem, I'm going to check the image list, take one image, check the label list, take one label, and give those two things together, the input and the target, the image and the label, to Pytorch, okay? That's what getItem does. And I could be doing imread here, okay? Instead of inputs, just taking the image from the image list and putting it into a float format. I could here first read the image from disk if I had stored the names of the images there, and then do the same, okay? Put it in the float format and give it to Pytorch, okay? If I did that here, every time Pytorch wants to access data, that would be a little bit slower because it would need to access disk and to read the image that it's reading, okay? And that's why in this case, we start by storing everything in RAM memory, by reading everything in the preparation step, in the init method, okay? What's the catch? Well, if our problem is big for the RAM memory of the computer that we have, and that happens a lot, okay? We might run out of RAM memory. There are different memories in my computer. Disk memory is usually very big, very large, but slower to access, okay? It also depends on the type of disk that you have. If you have an SSD, a solid state disk, that memory is also quite large and also very quick to be accessed, okay? But in general, I have RAM memory, which is a memory that's used for the things that are running in the computer at this moment. So it's more changing, okay? It's not meant to be long-term storage, okay? So in my RAM memory, I have things that I want to move about and to be able to access really quickly, okay? So if my problem is small enough, I can just put everything into my RAM memory like I'm doing here, and then when Pytorch wants to read that data, then that's much quicker, okay? So if you have a bigger RAM, you can read everything from the start. If your RAM is smaller, your problem is bigger, you might want to read here and that will make things a little bit slower. Okay. This getItem method is very simple, but well, you have to be aware of how Pytorch is using that. Pytorch is using this to make batches of data. So the whole point of using Pytorch is to be able to use the GPU and to do these optimization calculations in the GPU. Those are pretty simple, but there are many of them. And those can run in parallel in the GPU. But in order to do that, I have to be able to arrange my data also into parts that can be fed bit by bit, pun intended, into the GPU. Okay, so in order to be able to take my images and break them down into part of the desired size, and then also group different images so that I can process them together in what's called batches, then that's why I need to use the dataset class, and that's why I need to use the getItem class, getItem method. Okay, init to prepare things and getItem to decide exactly what I'm going to be giving to Pytorch to process. Okay, so that's my final, let's say, go at the dataset class and how you have to use it for task number 2. Okay. But then today I wanted to talk about a little bit more about models and model fitting. Let me check for a second in case there is any question. You can, of course, ask any question if you want. I'm going to check Slack and web class forum. The explanation was a little bit long. Okay, no questions at this moment, so no problem. Moving on, we are going to be speaking about fitting and training deep learning networks. And this is the reason why I am pretty sure that we are not getting intelligent killer robots anytime soon, and why I have a reasonable suspicion that we are heading towards another AI winter, or at least AI cooling, probably sometime soon, because at this moment AI is very much on fashion, and there are lots of people taking the opportunity to make some money by promising lots of things related to AI. And I think this is a very exciting time to be working on this, and this is a very useful technology. Okay, that's why I'm teaching this class and other things. But at the same time, one has to be aware of what it is that we are doing and what are the limitations of the whole thing. I think AI has already had a significant impact in research. I used to do lots of research in medical imaging. I'm still doing some, and when I was doing that during my PhD years, a few years ago, AI was just one more tool. It was before the, let's say, deep learning revolution. Okay, it was one more tool, and if you had lots of time and lots of data and a very good team, that could be very useful, but it was difficult to use and it took a long time. But since then, maybe at the time, the percentage of papers that used AI was, I don't know, 5-10%. So some of them, but not many of them. Nowadays, if you not open anymore, download any issue of the best medical imaging journals, you will find a very high percentage of papers that use AI. So AI, and very particularly deep learning, have changed the way research is being done. Not only that, they have created some products that have had some significant impact in our lives already. Okay, so we are all getting all of these algorithmic recommendations which have a significant let's say, presence in our everyday lives. And we have ChatGPT, which is something that's interesting, even though I don't think ChatGPT is going to change the world. What might change the world soon are other applications of AI, like, for example, self-driving cars, or I think automatic translation has already had a significant impact and will probably continue to get better and to do so. Okay, so I definitely think AI is an interesting technology, and it's a very useful thing to know about and probably to have in your toolbox, whatever you're working in. Having said that, it's also very, very limited. I'm very interested in the subject of what's called AGI. So artificial general intelligence. Okay, will we get anytime soon a computer that thinks like us? And I'm sorry to say, so far everything I have seen is smoke. Okay, I don't think we are at any moment even approaching that. Okay, we have deep learning networks that do very narrow tasks very well. And if we have problems that are nice for the task that we are working with, and if we have good enough data, then we can do lots of things. Okay, and with deep learning networks, that has become much easier than it was before. So there has been advances. But that's, in my opinion, not intelligence. And in my opinion, it will not be, because all deep learning networks do is optimize models that reproduce patterns. Okay, what I'm doing here is something that the fast AI guys call making neural nets uncool again. Okay, these models, deep learning models, making them uncool. I guess these guys from the University of San Francisco, and I heartily recommend this course, okay, or these courses, because they are very good and they are online, and at least last time I checked, they are for free, okay, in Pytorch too. These guys are trying to also demystify the whole thing, really explain how it works so everyone can understand its limitations and its strong points. Okay, so after having recommended these courses too, if you're interested, lots and lots of very long online lessons too, I'm going to excuse me, I'm going to speak a little bit about the details of how deep learning networks work and do my bit to making them uncool, okay? Deep learning networks, in short, do the same as linear regression. Okay, in linear regression, and I have a notebook here that does linear regression, we have some data. And here, the first thing that we do is generate that data. Okay, so I'm just using this function where I generate polynomial data, and I give it a number of coefficients, and then I use those to generate something in polynomial terms, okay, with adding an exponent to the x and then reading from a coefficient list. So this is the coefficient of the term 0, and this is the coefficient of the term 1, and so on. And because I only have a list with two coefficients here, I'm generating something that's linear. By the way, with linear data, what I have is something that's governed by those two parameters, these two, okay? And the second one is the slope of the line. So if I do this one, and let's say this one, what I'm getting is a line that goes through 0 and has negative slope. So I will have something that's like this, okay? Okay, so I can generate any line that I want here. And my job in the linear regression world will be to fit a line through this data. find a line that's as close as possible to this data. Okay. So here I have my data. My model will be a line. So it will be something like this that will have two parameters. Okay. So I could generate other data. Okay. For example, here I'm generating quadratic data or cubic data with the same function, and I could do whatever. Okay. But what I want to do initially in linear regression is to fit just one line through this data. Okay. And now let me introduce the terminology here. I have my data, that one we have already, but my line will be my model. Okay, and these two arguments, the slope and the independent term, will be the parameters of my model. When my model is a line, a very simple one, it only has two parameters. Okay, so I will want to fit my model through my data, and I will want to know what possible line is better. Will a line that's here be very good, or will this be better, or will something like here be better? I have to decide what better means, what being close to my data means. And most of the time, what is used is for regression types of problems, minimum squared distance. Okay, so for every data point and each of the points in my model, so if I have a line, I will come here to each point and see where my line crosses, and I will have my model point, my predicted point, and my data point. And I will compute the distance between my predicted point and the real points in my dataset. Okay. And what I will want to do is make this function that tells me how far I am from my data, this loss function, as small as possible. Okay. I want to find the minimum, as small as possible is the minimum value of the loss function. Okay. The loss function will be the difference between my model and my data at every possible value for the parameters. Okay. Let's see this visually. So I'm going to define a model. First of all, I'm doing linear regression. So I'm defining a model that like I had before. The A for the linear term and the B for the independent term. Okay. And I'm going to have some functions to just see in one initial random position of my model, see it with my data. Okay. Now I want to move my model so it's as close as possible to my data. Well, to optimize this loss function. Okay, I want to find the minimum of the loss function, which is defined as the distance from the model to the data in terms of that minimum square distance that I saw before. Okay, so I will define a function called fit, where I will receive my line, my parameters for this moment, the position exactly where my model is. So these two things will be the shape of the model that I had here, but also the position where the model is at this moment. Okay, and then I will have my data, X and Y true, and the number of epochs, the number of iterations that I want to do. I can even pass my loss function as a parameter. Okay, because I could use different loss function. I usually use minimum square distance, but I could be using something different. Okay. This fit function will be an iterative function. So I will have a for here. I will do these things as many times as you tell me, as many epochs as you tell me. Okay. Each epoch is an iteration where I run all of my data through my model and I try to generate new parameters to fit my model better. Okay. And I always do it in the same way. For each epoch, I make predictions. So I find the positions of the points that I'm predicting with my model. okay? Let's go back here, for example. So what this means is that if I want to predict what the value for my data for my dependent variable will be for my x parameter value minus 0.25, I go here and my value is something like minus 0.25, okay? Sorry, 0.5 probably, okay? So I come here and I predict my values. For each value of my model, I can predict one value of my function, okay? Of my data. So the first thing that I do is I make predictions. If my function was something different than a line, I would take the adequate value for x and get the adequate predicted value for y. Okay, and I need to do it with the model and with the current parameters of the model. Then I compute the loss. I compute the minimum squares distance in this case between the predicted points and the real y points. Okay, and then we store that. That's what we are going to be doing. At every point, I'm going to be predicting and seeing how far I am, computing the loss function. But not only that, then the third thing that I want to do is compute the next set of parameters. I want to use the information that my loss function is giving me. Am I far away? Am I closer now? Am I further or closer than I was before? Okay, I want to use this information to generate the new set of parameters. This direction in which you are moving is okay. This one is not so good. Okay, so my fitting loop will always be the same. I will have a number of epochs. I will make predictions, compute the loss, and use the loss to compute the next set of parameters, and then iterate. Okay, so here, basically, I have initial version of this generation of the parameters, okay? And here we have the very, very important backward word. But before I get to it, let me introduce the learning rate, okay? The learning rate is usually well-known hyperparameter of the fitting of deep learning models that basically governs how big my steps are when I update my parameters, okay? So let's not get too deep into it, but this is the learning rate, okay? I said, in each epoch, in each iteration, I'm going to make predictions, see where my model says the data should be, and then compute the loss between those predictions and the real values of the data, okay? And now I'm here where I'm updating my parameters using this loss function, okay? So what I'm going to be doing here is this optimization. The backwards word means that I'm doing the derivative of my loss function, okay? Why am I doing the derivative of my loss function here all of a sudden? Because as I showed before very briefly, what I want to be doing is optimizing, finding the minimum of my loss function, okay? Of the difference, of the loss function of the difference between the data and the model, okay? So what I will be doing in this case, this loss function will depend on potentially on many parameters or many variables, okay? So I need to do the derivative, or if I have more than one variable, which will very much be the case for most model, I need to do the derivatives, the partial derivatives in terms of the many variables that exist, okay? And use those to compute the minimum of the loss function, okay? So because my model, in this case, my model is very simple, okay? Sorry, my model is a polynomial linear thing. For example, this one, okay? My model is very simple, so computing the derivative in this case would be very simple. But this is general. I'm using a code that works with different types of models, and the structure that I'm using is the same exact structure that works for fitting and for training deep learning models. So this model here that I'm using a line as an example, but this could be anything, and this could be potentially and is a very, very complex function. So finding the derivatives of that might be a bit of a nightmare, okay? By the way, the backward word comes from the fact that when I have functions expressed as matrices, the inverse, the derivative of the function usually includes the inverse of the matrix. Okay, and that's why I have to go backwards, because the inverse is usually applied in the inverse order, in the backward order to the direct function. Okay, if you have done some numerical derivation, numerical differentiation, or numerical methods, you probably already are familiar with this relation between derivatives and inverse functions and this application in the opposite order, in the backwards order. And if you're not, don't worry too much about them. Okay, let's say it's a technical thing. But in general, when I want to apply my model, to use my model to data, I use it forward. And when I want to optimize it, when I want to compute derivatives, I have to go backwards because I have to apply things in the opposite order. Okay, that's why the first thing that I do here is do this backward to my loss to compute the derivative of my loss function. Okay, and then I update my new parameters with something that depends on the learning rate. Okay, and on the results of this backwards. Okay, this loss backward moves through the network on this backwards direction and updates all of the derivatives of all of the small parts of the model and stores each of them in this gradient. That's where the derivative comes from each node. Okay, so that was very technical, and this is very technical. This is high school math in the sense that in order to find the minimum function, you need to find the derivative. A little bit numerical programming in the sense, numerical methods in the sense that we need to know a little bit about these things of computing the derivative is the same as computing the inverse, and that's the same as going backward. So that got a little bit technical, but what we are doing here is just predicting, computing the loss, and then doing this derivative of the loss to update the parameters, okay? And once we have the backwards, we want to have the derivative, then there are different ways to use that derivative to update the parameters. Usually we have an optimizer method here that might work in one way or another, and in which we don't have to worry too much about because we will have many to choose from in our Pytorch library. But this is the reason why the main module, the main part of the Pytorch library is called AutoGrad, auto gradients. Deep learning libraries are nothing but automatic derivative computation libraries. And training a deep learning network, teaching a computer to classify images, to segment images, to do regression, to find objects in images, training a self-driving car to detect pedestrians in images is nothing but having a model compute lots and lots and lots of derivatives. That's why all of the deep learning libraries are basically gradient derivative computation libraries. Okay, that's the making them uncool part. All we are doing is defining a function that, in the case of deep learning networks, is very big and has many, many, many parameters, but then we're just optimizing it, finding the minimum, not exactly of the model, of the loss function, of the difference between the model and the data, the predictions of the model and the data at each step, okay? And that's exactly the same that we were doing in linear regression. Okay, so let me have this fit, and now I'm just going to be running the fit function for a few epochs, in this case 15,000. Okay, and here I get a fit for my data, a linear fit, which is probably pretty good because, well, in the very limited model that I have, this is probably the best way to approximate this data. Okay, if the data behaves nicely and is linear, yeah, I'm already more or less fine. Here I'm plotting, for example, the loss function in terms of the number of epochs. Okay, this is useful. Here I see that my loss function has been going down, 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 down. So I have success in this optimization problem. Okay. One of the things that many people do not properly understand, many people using deep learning these days, is that this is a purely mathematical problem. Okay. I'm just optimizing a function. In deep learning applications, my data will come from some real problem, and we will hope that by fitting a model to the data, we will be creating something that is useful to solve the real problem. Okay? But what we are solving is a mathematical problem. What we are optimizing is a mathematical function. Whether or not that actually helps with the practical problem of classifying tree images or detecting people in a car images or detecting trees in a drone image, whatever that really helps is dependent a little bit in how this optimization process went, but so much more on how we handle the data and whether or not we were able to make our models in a way that then is actually useful for practice. And more about that in the next sessions. Okay. Okay. I'm not going to be running that because it takes a little while, but let me show you the video that I made before. This is a iteration by iteration plot of one previous set of data and seeing how that works. Okay. As this is being pretty, you can see that the initial steps are longer, are bigger than later steps. Okay, and now things is still moving, but it's moving slower. Okay, let me just check it again. As you can see here, it's pretty easy to see that the line is jumping quite a lot. But once we are here, the movements are much smaller. Okay, that happens with the training of deep learning networks, and that is important because that means that the initial steps might sometimes sidetrack me if I have had some bad luck with my data and I'm seeing some data that is atypical, infrequent in my initial steps. Okay, that's sometimes called that my training might get stuck in a local minima. Okay, more about this later. As I was saying, this is a little bit dense, so I'm going to make hopefully a little bit of a shorter session today. But let me give you a couple more deep hints now. So the first one is that I need a model that's adequate for my data. And a very, very simple way to show this is with this example. Okay, I'm fitting again my model to the quadratic data that I generated before, and I get a horrible fit. Okay, even though my fitting function is the same, the problem is that data just does not have linear shape. So I'm trying to use a model that's not adequate for the data that I have. Okay, and if I plot that, I get something. Oh, I still get optimization here. Okay, that shouldn't have happened so nicely. Well, I'm wondering if I'm overriding the variable here. Yeah, I had to overwritten the variable. So I get a pretty shitty fit, and I get a loss function that doesn't grow, okay? What was happening is also interesting because sometimes I get some pretty unintuitive readings from loss functions. So do not trust loss functions too much. Okay, we will say a couple of ways in which they can be used, but they are, as I was saying, they belong to the theoretical problem. If your aim is solving something practical, loss functions have to be handled with a little bit of care. Okay, and well, in this case, it was very simple. We could create a quadratic model, and with exactly the same fit function, we can now fit our data, our quadratic data too, and so on and so forth. Okay, here it's led as an exercise to do the fitting for a cubic model with 3 parameters. The type of things that can be fit with this type of functions are many. Okay, for example, here we try to fit these sets of squares into each other. Okay, and you can have a look at this, but basically we are using the exact same fit function. Fitting a model just means, as we said before, sorry, I'll be there in a moment, making predictions, calculating the loss, and using the loss to generate the new parameters. Okay. Let me go for a second to the last unit for the moment in the course, training deep learning models. Okay, this is one that you can mostly use as is if you're doing image classification, and need to modify just a little bit if you're doing semantic segmentation and object detection. Or regression. For regression, you can use it pretty much as is. Okay, my point here is that and please have a read at that, I'm using lots of code, I'm again generating the data set, and I'm defining a model, okay? Here, I'm defining a model by just using a predefined ResNet 50 models. ResNet 50, we saw it a couple of weeks ago in the ImageNet competition in 2015. It was a model that went beyond human capacities in image classification. So a very well-known model, already 10 years old, and still, even though not state-of-the-art, not one of the best around, still pretty decent and very convenient because it's smaller than other models, so we can use it in Colab. Okay, so I'm just defining my model by using Pytorch capacities to copy the structure of the ResNet 50. And you can check exactly the structure of the ResNet 50. Not anything super complicated, but if I had to define it by hand, it would take a while, okay? Because it has many layers. It's a deep learning model, okay? And then I'm even reading the weights. The weights are, I'm reading the weights in the first line and defining the model in the second. Okay, in the first line, I'm reading the ResNet 50 weights, and in the second one, I'm defining the model to fit. The ResNet 50 weights are the values of the parameters, the weights, resulting from training the ResNet 50 in the ImageNet dataset. Okay. So I'm starting my model not with random parameters like I started the linear regression, but with the parameters used to solve that ImageNet competition. Okay, this is what's called transfer learning. I'm doing that because I hope that those parameters will help me also classify trees. The ImageNet database has is an image classification data set, and it has many classes with many different things depicted on them. And the species of trees or species of supple pine bushes in Japan is not one of the things of the classes that are there. but there are different classes. And the hope is that in order to classify those classes in the ImageNet dataset, I will need to do things like separate things and find boundaries and find textures and find colors. And maybe that is already encoded in the parameters, and maybe that can help me solve my problem. Okay. So here I have an example of something that intuitively is usually expressed as, by using the solution of a similar problem, I can now solve my new problem using less data, because I am transfer learning. I'm using what the model learned before for the new problem, which sounds kind of mystical, but means actually, instead of starting with random weights, with random values for my parameters, I'm going to start with these values that maybe they help, because maybe some of these parameters are already doing tasks that I'm going to be using again. Okay. So this is complex in the sense that it has many pieces, and I will probably never know exactly what parameter is doing what and what parameter I'm reusing more effectively. So it has a component of, we don't exactly know how this works, which is something that's very often said when speaking about artificial intelligence, and again gives it part of its mystical aura. Okay, we are not sure exactly what it is doing, is something that people who want to make this sound more important than it is often say. Okay, that's true, but it's true in the same sense as we don't really know what our car is doing. Okay, we have a general understanding of how our car engine works, but usually we don't open the trunk and check and see how everything is connected and how everything is working. Okay, so this is a similar kind of things. We absolutely know what each node does. We put them there. We created the ResNet 50 architecture. Okay, and maybe you have not looked at it and so on, but you can, and that's all completely defined. Okay, we are not exactly sure what value is helping us the most, what part of our model has each effect on each of the answers that we are getting. But we could also track that. The point is actually not to do it. We have models that are very adaptable, that are very general, and we don't want to precisely have to define the small things that are done ourselves. We want to leave it flexible and to adapt them in a general way. Okay. So again, making neural networks uncool. They do lots of cool things. They are not usually followed to the smallest detail, but that's kind of the point. And that doesn't mean they are magic. They mean they're complex, they have many pieces, but they are not thinking by themselves, and they have no mystical powers. Again, sorry, no killer robots anytime soon. Okay. So here I have defined a model, not one with 2 parameters like I did with linear regression, or 3 with quadratic regression, but one with millions of parameters. But when I want to train that model, lots of things in between, I get exactly the same structure as before. Forward pass or make predictions. Okay, and the syntax is different because I'm using my model. I'm actually using my model in the exact same way, but I'm using some functions from Pytorch in between. I'm using my loss function exactly in the exact same way I was doing. So this is step 1, step 2, and step 3. Again, backwards and calling an optimizer to create the new values for my parameters. Okay, so the fitting function is exactly the same as I did for linear regression in Pytorch. Make predictions, compute the loss function, use the loss function to create the new set of parameters. Okay, this is how artificial intelligence works. Amazing, many applications, no magic, no artificial general intelligence anytime soon. Okay, have a look at this in detail. Okay, there is a video for this. This is absolutely a nice thing to do next Monday if you're not traveling to Mongolia, and I will give you some more input on this. Okay, but you can use these functions I recommend a train validation function mostly on your own and as they are for most of the versions of the final project. Okay. Okay. And here we have some more training and results and so on and some analysis. In the remaining, I want to, of course, lend you all a hand with the programming of the third project, because all of these things are really nice and really theoretical, but this only works if you get your hands dirty and you get some feeling for the results and what AI can do and cannot do for your project. But before I finish the course, in the time that I have left, I want to speak a little bit about overfitting and about the difference between the training, testing, and validation. The difference between these two theoretical problem about optimizing network and computing all of these derivatives and so on and so forth, all that good stuff. But then the practical problem. How do these two connect, and what happens if you don't connect them properly? Okay. So that's all from me. And as I said, this is pretty dense, so I'm going to stop here. But before I do, let me check whether or not there are any questions in web class or in Slack. Not at the moment. I don't know if any of you has any questions for me right now. Okay, so apparently no questions at this moment. Keep them coming. Email, which is mostly the way most of you use, but also in Slack or in web class about general things. If there is any specific thing that you want to talk about or hear me talk about AI related, they can be very particular things and specific things and technical things if you give me some time. But also if you want to talk about general things, something that you have read that you're interested in, worried about, whatever, just keep them coming. And of course, work on the third project. Many of you have already lots of points from projects number 1 and 2, but I think if you work a little bit in project number 3, you should be able to get a really nice mark for the subject. And that's, I think, what we should all go to. And that's it for today. So thank you very much for listening. Next week, no class at this time. I will give you some reading materials in web class, and then we will go from there. We will be having a class in 3 weeks' time for sure, and we might have some additional contents a little bit before that. Read web class to get all the details. Thank you very much.